All right, everybody, 10 o'clock, ready to rumble. Yes. Welcome back to your favorite class. Yes. All right. I'm getting some head nods. That means maybe it is your favorite class. Okay. my theory is if I keep saying that, you'll eventually think that it's true, right? It's the Donald Trump method. Okay. Sorry, I shouldn't be political. If I keep saying it, you will think that it is true. Okay. A couple of announcements, which I did share on the screen here. I'll share it again really quickly. Today we're going to continue with principal stress conversation, stress transformations. A couple of announcements. Your rough draft, your first draft for the lab report is due right now if you're in the Tuesday lab, right now. And will be due Wednesday at the beginning of class if you're in the Thursday lab. All right, the purpose of this is not really to give you your full grade yet. I'm just trying to improve your writing, okay? So get that to me as best you can in what you think is like the final form. It'll save you work later also, which is also nice. And I will give you feedback as best I can to improve things like, your writing style, your presentation of the material, the technical side of it, do you have the right calculations and all this sort of stuff. I'm going to try to give you as much feedback as I can. Probably only do it this one time. So really make it nice and complete as best you can for this first draft. All right, so that's that. In lab this week, then, we'll have these like one-on-one meetings between me and you. They'll probably last about 5 minutes each, where I'll sort of highlight some of the things I think you could probably work on to improve your technical writing. Okay. So I sent out like a sign-up sheet by Google Sheets, so please take a look at that. I've also given the link on Blackboard in the Combined Loading Lab tab, so you can use that link there, or you can use the link in the email. Please sign up for a meeting time with me. Most importantly for the Tuesday people, because we're going to meet tomorrow, and then obviously the Thursday people sometime between now and then. All right. Finally, I've kind of peeked at a few of the lab reports already, and it seems that there's a little bit of confusion about what's going on with the strain calculations, specifically at like the side of the bar when you're calculating like shear strain for, let's say, like point B, which is kind of on the side of the bar. So this weekend I sort of made like a supplemental lecture on strains and strain calculation and how to do that at point B. I hope this will like clarify things with a little bit more pictures and strain transformations and what's going on with that strain rosette. It seems like there was some confusion, so there's maybe like a 20-minute video on some of that calculation. So if you're struggling with that, please go take a look at that lecture. That's also on Blackboard. There's a link to a YouTube video, so go ahead and take a look at that. All right. So hopefully that helps. Right. That is a lot of ado. I don't like all these ado. Is there any more ado? No questions? No in the chat? Okay. So then without further ado, let us ado some mechanics. Oh boy. I'm trying my best, okay? Try to like at least give you some entertainment here. Kevin Hart, I gotta live up to like the comedian name, alright? Not quite as funny as him, but I try. Okay. So last we left off, we were talking about two-dimensional stresses and two-dimensional stress elements. Looks like that projector is like twitching out a little bit. Is that like annoying you guys? Sorry about that, but we got some like projector issues in the room. But okay, last we left off, we were kind of talking about stress transformations in the stress element. All right, stress cube slash element. All right, and remember this stress cube that we had here sort of looks something like this. And it represented like the 3 orthogonal cuts we could make at any particular point in a material, and the 9 states of stress that might result from those 3 orthogonal cuts. If you have something here like XYZ, you could have your series of stresses, the normal stresses here coming off of each one of these faces. It's like sigma Z, sigma Y, sigma X, as well as the shear stresses that you could possibly have. I'm not going to label them all because it's kind of running out of, I'm a little short on space here. But you get the general idea. Here are the shear stresses Ij on all the faces. And remember, when we're talking about using subscripts Ij, we're talking about the I face and the J direction. Okay. So this is our stress cube and element, and I was relating this back to what you probably learned in 2004, which was like one side of this particular cube, which is like a two-dimensional element, okay? So a 2D element can be viewed by looking down any axis. Right? This is probably what you saw in 2004. And so if we, for instance, like looked down the z-axis, you might see something like this, right? Where we might have x, y. And you would see stresses coming off of this particular element. Here are your normal stresses in y. Here's your normal stress in x. Sort of on both sides. And then you have your shear stresses, which are acting on their appropriate faces and directions. So here's something like tau x, y. And all these shear stresses I've drawn here are more or less equivalent, right? So we know that on the top face you would have what is tau yx, on the y face in the x direction, but we're equivalent by conservation of momentum. All right. So those are your possible stress states on a 2D element, and here we're assuming plane stress such that all z component stresses are 0. All right, so that would be like normal stress in z and any shear stress associated with z. So tau xz, tau yz, tau zy, tau zx. All right, all of those components are 0, and this is probably where you did a lot of work in 2004 on an element that looked a lot like this. So I'm kind of reviewing this and going over this, and one of the first things I want to talk about is stress transformations, and so that's about where we left off. We were looking at, okay, let's say we have this particular element here, and we want to talk about the stress not in this coordinate system, but some alternative coordinate system that is rotated from this xy coordinate system some amount. Okay, so stress transformation. Okay, if we want stresses in alternate coordinate system, let's say ergo in nt axes in terms of sigma x, sigma y, tau xy, these stress values that we already know in our current coordinate system, and the rotation angle theta, which exists between the xy coordinate system and the coordinate system that you want to rotate to, which might be the nt coordinate system, that might look like this. Right? And so that angle theta here would be this angle theta. Sort of your counterclockwise rotation angle from x to n and from y to t. All right. So we looked at how to do this, and the basic way that we're going to do this is we're going to cut through our two-dimensional element, sort of along the t direction, to get what looks sort of like a triangular element. So cut through t-axis. And you're ultimately going to end up with some triangular element that looks like this here, where we still have sort of on the backside of our element the x and y components of the normal stress, and we're going to retain our shear stress on the back side in terms of what we know. And we have our coordinate systems. And let's establish our coordinate system sort of at the center of this cut section here, which is like x, y. And we have our new coordinate system, which is kind of coming off of this general direction, which is like n and t. Okay? So what we want, what we're striving for, is what is the normal stress on this new face that we have created, and what is the shear stress on this new face that we've created. So we're more or less looking for what is this sigma n, and what is the shear stress across this face, which is tau n t. I'll put these question marks here, because that's sort of what we're after, right? So we started in on this last time, and we kind of went through the derivation and said to find sigma n, we want to force balance in n direction. Right? So what we're doing in math terms, because we all speak math, is that the sum of the forces in the n direction is equal to 0. So what that means is we have to turn all the stress components that we see into force components, and then equate them all to 0, and see what we get. So we went through that rigmarole last time, and I'll wave my magic hand and point you to that lecture, which was in the Wayback Machine on Friday. We did this, and we established what this equation was. And this equation, generally, we found that the normal stress in the n direction after this transformation is sigma x cosine squared theta plus sigma y sine squared theta plus 2 times tau x y sine theta cosine theta. So this is the expression that resulted after we did our force balance to get you normal stress in the n direction in terms of stresses that you already knew in the xy direction and tau xy, as well as the rotation angle between your coordinate systems, which is the rotation angle theta. All right? So this is the stress transformation equation that is useful for telling us this new normal stress. Now, it is often presented in a different form, and that different form is using the double angle identity. So we can transform what is like a cosine squared term into like a cosine 2 theta term, and it's sometimes presented in that form. So I'll just write this without the derivation. Which you may or may not have used in 2004. I'm hoping you saw at least this equation, this what I would call the standard equation with cosine squared sine squared terms. Maybe you used the double angle form, which looks similar, with a couple of caveats. Sigma x plus sigma y on 2 plus sigma x minus sigma y on 2 times cosine 2 theta. And this is going to be plus tau x y times sine 2 theta. So this is the double angle form of that exact equation. These equations are equivalent. They'll give you the same answer, which regardless of which one you use. I think the double angle form's on your equation sheet, so maybe that's the preferred generally, but I present them both here just for clarity's sake. All right. Both of these equations can be gotten from sort of the force balance in the n direction. All right. Now, we could go through a similar sort of procedure with a force balance not in the n direction, but a force balance in the t direction. Okay, so we've calculated what is sigma n. If we go back to our element up here, that's kind of a check mark there for the sigma n. But now we also want to determine what is this tau nt term, all right, which is this, shear stress across the face. And to do that, we see that the shear stress is mostly aligned like in this T direction. So it's on the N face in the T direction, so we're going to do a similar sort of thing, where we do a force balance not in the N, but we do a force balance in the T. So I'm going to kind of gloss over that. So for tau nt, use sum of the forces in the T direction equals 0. Good old statics, right? Some of the forces in one direction, we still got some of the forces in the other, baby. Let's go. Could also do some of the moments, but since this is an infinitesimally small element, we don't have any moment arms, so that's not really helpful. All right, so it's a similar idea, similar derivation. I'm not going to go through the whole derivation. I'm just going to present what is the final result. And that is if you need the shear stress in this alternate coordinate system on the N face in the T direction, you're going to have negative quantity sigma x minus sigma y times sine theta times cosine theta. And this will be plus tau xy times cosine squared theta minus sine squared theta. All right, this is the single angle form. If you're feeling really antsy, you can derive this yourself, and I'll be very impressed. I'll give you a gold star. I'll literally go to the store and buy some gold stars and give them to you. Or if you want the double angle, I have to be very careful when I spell angle that I don't write angel, the double angel form. All right, instead of L-E-E-L. You guys ever seen that tattoo where the girl has like guardian angle on her arm instead of guardian angel? It's hilarious. Like misspelled angel, just guardian angle. Oh god, that's funny. All right, so the double angle form is going to be the negative quantity sigma x minus sigma y. All this on 2 times sine 2 theta. And then this is plus tau xy cosine 2 theta. All right, so this is the double angle form. All right. Now, why would these stress transformation equations generally be useful? Well, you've kind of already seen an example of how it could be useful in your lab. So, we have these strain gauges that are plopped onto your piece. And let's say the strain gauges give you some strain reading in some direction and you convert that to stress in that direction. But, the stress that you have with that coordinate system is not necessarily the coordinate system you want. You might have to do your stress transformations to get you to the coordinate system that you care about, and this is how you might do that. Right? So, now that we've presented these equations, let's look at an example. And we'll plop that in here. All right. Give you a second to copy it down. And we'll go through it. This is where I would take a sip of my coffee. I remember those previous times when I could have drinks in class. The good old days. I just have to be up here all not drinking my coffee. What was that? Well, I'd have to take my mask down and just, I don't know about that. It seems a little suspicious. I get like a straw through. Sounds like a good solution. Just like coffee, which is a good solution. Or is it a suspension? I don't know. I think it's a solution. It's been a while since I've had chemistry, so I don't know. All right. So keep copying it down if you are. I'm gonna take this picture and just plop it into the notes, okay? So if you got it, keep going. If you need to keep copying, keep copying. All right. Let's get this bad boy in here. Bam! All right, so here's your picture. We want to find normal stress and shear stress on AB. So that is sigma n and tau nt on plane A, B, A, B. Yes. That's kindergarten. Yes. All right. So we're going to utilize our equations here, but I want to just write down things that we know and present our element accordingly. All right. So some things that we know straight away here. So first would be like what we know. So we know that we have a stress in the x direction, which is what value? Someone in the audience. 80 megapascals. Good. 80 MPa. We have a stress in the y direction. Somebody else. What value? Negative 100. Good job. Gold star for the day. All right, it's negative because we're in compression here, sort of pushing downwards. And then we have a shear stress, tau xy. Who wants to tackle this one? Positive or negative? We know the magnitude's 60. Positive or negative? Anyone else? Negative. All right, you're 1 for 2 on the day, so all right, that's good. So why is it negative? Let's talk about why it's negative. So here's our arrow for the 60 MPa. We'll notice that it's on the positive x face and the negative y direction. Okay, so positive x face, negative y direction. So this is going to give me a net negative, okay? You could look at any of the arrows and identify that. So here, this arrow, you're on the negative y face, positive x direction. All right, this arrow here, positive y face, negative x direction. They should all give you that same idea. Negative x face, positive y direction. All right, so hopefully we see that and understand that. So I'm going to get a net negative from this shear stress. All right, so now if I cut through AB, just like that, this is the cut that I'm going to have. I'll create an element that looks triangular, kind of like the one that I have shown previously. So let's take a look at what that element will look like. And let's assign our coordinate system accordingly to make sure that we have the right rotation angle for this problem. All right, so here we are with our standard coordinate system, our x and our y. And we want to know basically what the normal stress is in this direction. And we want the shear stress on this face as well. So we'll define our t-axis, and we want nt. So we know that the equations that we're about to use will utilize the variable theta, which is the rotation angle between the xy axis and the nt axis. And so we need to define ourselves what is this angle theta. Right. And this can be a little trippy sometimes, so be mindful. So we're given information about this cut, specifically this 48 degrees here, which is sort of, I don't know, from the horizontal at the top. So if I wanted to sort of like represent this on my triangular element here, maybe that's this angle here is 48 degrees, equivalent to the temperature of my heart. Okay. So that means that this angle is also 48 degrees down here. So the angle that is theta here will not be 48 degrees, but will be the complement of 48 degrees. You're such a good-looking angle. Okay. It's complementary. And so here we have 42 degrees. All right. So in this particular problem, we're going to use the value of theta, it's 42 degrees, to get our appropriate transformations. All right. So away we go. It's probably the hardest bit is just defining the stress components correctly. I'll use the double angle formula here because, why not? Reminder, that's sigma x plus sigma y on 2 plus sigma x minus sigma y on 2 times cosine 2 theta. And then this is going to be plus tau xy sine 2 theta. All right. Now all these values we have, I'm just going to go ahead and plug and chug them. And just a reminder, I'm just going to work in MPa. I'm not going to write MPa with every single entry of the stress. Just understand I'm working in MPa here. This is going to be 80 minus 100 on 2 plus 80 plus 100. Remember that sigma y is a negative value on 2 times cosine of 2 times theta. 2 times 42 is 84 degrees. I did that in my head. What's up? All right. Plus my negative 60 sine 84. All right. So then the normal stress on that cut face after sort of working through this will be negative 10 plus 9.4. I'll just kind of show each of the contributions accordingly. Minus 59.7. Still working in MPa. Will give me a total normal stress on this particular surface, negative 60.3 MPa. Okay, so that's the normal stress on that cut face. All right, now the shear stress. Similar idea. These are equations that are derived from summing the forces in the t direction. Negative sigma x minus sigma y on 2 times sine 2 theta. And this will be plus tau xy cosine 2 theta. All right. I'll assume you can plug values in here. Again, we'll use the same values for sigma x, sigma y, tau xy, and theta. You should end up with negative 95.8 MPa. Okay. So that's how do we utilize these stress transformations. All right. Now, one quick question I just want to go over that I sometimes get is, yeah, we figured out what the normal stress is in the n direction. What if we want the normal stress in the t direction? Okay. What's our method? Anyone suggest some method? It's simplistic based on what we already have. What would be the normal stress in the t direction?
Would you just add 90 degrees?
Yes, perfect. Person in the chat says add 90 degrees to the angle of theta. That's exactly right. Right? So if we have x and y, and we have n and t, we know that this angle here is theta. We know that this angle here is theta plus 90. Jeez. Theta plus 90 degrees. Okay? So sigma n I get with the angle theta. Sigma t, I could use the sigma n equation, but with the value for theta of theta plus 90 degrees. So instead of using theta, use theta plus 90. So in this example, instead of using 42, use 132 degrees. This is how you might go from stress in like an xy coordinate system to an x prime y prime coordinate system. Right? All right, cool. Let us continue. And thank you for whoever said that in chat. I didn't catch who that was, but good job. All right, those are your stress transformations. Next topic is principal stresses, something you probably should have discussed in 2004, but again, sort of building up the foundation because I don't know how the 2004 went for you guys. All right. And I also like to have this conversation too because we're doing all this in 2D right now, and we will do this in 3D. So yeah, it's gonna be instead of slicing through a 2-dimensional square, you're gonna slice through a 3-dimensional cube. Hot diggity. All right. And see what happens in that situation. All right, principal stresses. Let's just talk about a general concept first. All right. So remember that we have this general equation that tells us what the normal stress is in any arbitrary direction. Okay? So with transformations that look like the following, I'll write the single angle formulas. Okay. So with these general equations, cosine first. All right, with these general equations, we could see that the normal stress in any direction is going to change as we rotate or look at the values of the normal stress in different coordinate systems. So if we're starting at some xy coordinate system that we know, and we just rotate through and look at, all right, what is the normal stress at 5 degrees from that, 10 degrees from that, 15 degrees from that, etc., you'll understand that the normal stress and the shear stress in each one of those general cuts that we make is going to be different based on the value of theta that we have. Okay? That means that if these values are sort of changing as we sort of swipe through and move through the rotation of our coordinate systems, there is some rotation angle that will maximize and minimize the normal and shear stresses that we see. Okay? So we might then pose the question is, at what value of theta are sigma n and tau n t max or min? All right. How do we do this in a calculus way? Someone, if you're asked to find the maximum or minimum of a function in calculus, how do you do this? You guys all took Calc 1, right? Right, set what equal to 0? The rate, right, that's good. We'll take the derivative and set it equal to 0. So in this particular situation, what we're doing is we're looking at various angles of theta, and as we change theta, the value of sigma n and tau nt will change. So we have functions here. These guys are both functions of theta. So the idea here is if we take the derivative of these functions with respect to theta, set that derivative equal to 0, that'll give us a value of theta which maximizes or minimizes these particular functions. That value and that rotation angle is the principal rotation angle for maximum shear stress or principal stress. Right? So here's the idea. So to find, take derivative, set to 0, and find critical angle. I'll call it some critical angle theta p for some principal rotation angle that will get us to that point of maximum or minimum normal stress or shear stress. All right. Oh boy. Wow. Take derivative, set to 0, find critical angle theta p. So in math language, which we're all more comfortable with, I speak math. That is, I want to take the derivative of these functions. That is the derivative of the normal stress, which is a function of theta. So the derivative of the normal stress, which is a function of theta, with respect to theta, set it equal to 0. Right? Also, I want to take the derivative of this shear stress transformation equation, which again is a function of theta, and set it to 0. Each one of these derivatives is going to get me a principal value of theta, which will maximize or minimize the value of sigma n or tau nt. Okay? Those maximum values of tau nt or sigma n are going to be your principal stress values. All right. Give principal values and max shear stress. Something like that. Okay? That's the general idea. So let's execute with what is sigma n, a function of theta. Well, d theta n t theta. So the derivative of the normal stress with respect to theta can sort of pop up here to our double angle, or sort of our standard form. Reminder here, this is the equation I'm taking the derivative of here. It's our transformation equation. Right? So the first derivative of this with respect to theta, okay, well, we can just go through that. So the derivative of cosine squared theta is, I think, pretty straightforward. You can either do this with single or double angle identities, and we'll just say here and go through it that you're going to get. After executing this, I guess this is the derivative of the double angle form, but same idea. Probably a little easier. All right. here's your derivative from double angle form. And a reminder, we're going to set this equal to 0 so that we can determine what that value of theta is that maximizes or minimizes this function. So let's divide everything by cosine 2 theta. And you're going to have something like negative sigma x minus sigma y times tangent of 2 theta plus 2 tau xy, 0. All right, we're trying to isolate theta, so let's continue. Or finally, this principal angle that will give you the maximum normal stress and the minimum normal stress, because right, the derivative set to 0 will give you maximums and minimums. So your principal angle, which I'm going to call theta p, after working through, is going to be 1/2 the inverse tangent of 2 tau xy over sigma x minus y. So this is how we calculate the principal rotation angle to get us maximum and minimum normal stresses. Okay? All right, on the domain 0 to 360, how many answers will I have for the inverse tangent function? 2, thank you. One for a maximum and one for a minimum. All right, that's good. All right, so 2 values on the domain 0 to 360 degrees. All right, sweet. Now let's take that expression for the variable theta p. We're going to now plug that back into the stress transformation equation. All right, so remember, if you're trying to find the maximum value of a particular function, take the derivative set to 0, plug that value that makes the derivative 0 back into the original function to get your maximum minimum value. Okay, so plug theta p back into your transformation equation. All right. This will give you, and I'm not going to go through the derivation because it's actually quite a bit of math. You're working with inverse tangent functions, which gets plugged into like sine and cosine, which, you know, barf. Okay. You'll end up with an equation which should look familiar. Sigma 1, 2, this is how we denote principal stresses, equal to sigma x plus sigma y divided by 2, plus or minus the square root of the quantity sigma x minus sigma y on 2 squared plus tau xy squared. Raise your hand if you've seen this equation before. Yeah, okay. Everybody's hand should be in the air. And you should wave them around like you just don't care. All right? So here, this is your principal stress equations. These are the values of max and min sigma n. All right. Maybe you saw this clearly defined in 2004, maybe you didn't. Maybe you saw where this came from, maybe you didn't. Hopefully, after my explanation, it's pretty clear where it comes from. We have these stress transformation equations, take the derivative, set to 0, plug that back in. There you go with your principal stresses, right? I go through this process because we're going to mimic this process in 3D, right? When we go to 3D, you're going to have an equation for stress transformation for any arbitrary plane that we can create with a normal direction defined by unit vectors, okay? Complicated. We're then going to take the gradient of that equation, which is the three-dimensional derivative, to determine what is the principal stress in 3D. Who's scared? Are you guys scared? I'm scared. Yeah. I'm the teacher. I'm scared. Okay. All right. So I go through this process in 2D so that we're all clear on what's happening. Then when we go to 3D with gradients and everything and you're crying, at least you understand what's going on. Okay. You don't know how to do it, but you know what we're doing. Okay. Similar process for shear stress. The idea here is that we take the derivative of tau and t, which is a function of theta. Again, our stress transformation equations, but now for shear instead of normal stress. Take the derivative with respect to theta. Here we're going to have negative sigma x minus sigma y cosine 2 theta plus 2 tau x y sine 2 theta. All this equal to 0. We're setting the derivative equal to 0. Right? We can again go through the same rigmarole. So we divide by cosine 2 theta. Again, I'm using this division sign I haven't used since 1997. Okay. Before you guys were even born. Okay. No, I'm just kidding. Maybe some of you were born. I don't know. I'm old now. And we're gonna have something like 0 is equal to negative sigma x minus sigma y plus 2 tau x y tangent 2 theta. Continuing downward, we'll isolate theta, and you'll end up with theta is, again, equal to 1/2 tangent inverse of negative sigma x minus sigma y. Sometimes you see it as sigma y minus sigma x, kind of the same thing, over 2 tau xy. Usually we'll label this particular principal angle not with a p, but with a tau. And that's because it's for the shear stress. Okay. Principal rotation angle for max, min, tau, and t, or what's sometimes called tau max. I see it as tau max. So let's take theta tau back into tau and t as a function of theta. And you'll end up with the following expression. Tau nt, or what I'll say is tau max, is equal to plus or minus the square root of sigma x minus sigma y divided by 2 all squared plus tau x y squared. which you'll notice is like the second half of the principal stress equation. Okay, hopefully we've all seen this equation before as well, right? This is your radius of your Mohr's circle, if you like that analogy. I personally think Mohr's circle belongs in the trash can, but you know, that's discussion for another time. I don't do Mohr's circle in this class. I think it's a waste of time. So if you like Mohr's circle, maybe you can do it. I understand it if you write it on your paper what you're doing, but you're never going to see it out of me, all right? I speak math, I don't speak circles, all right? So here's your maximum shear stress. Again, can be gotten from the angle here, just plugged back into the equation for tau nt. On 0 to 360, again, you have two solutions. One will give you a positive shear and one that will give you a negative shear, but the magnitudes will be the same, right? So there you go. All right, when we come back on Wednesday, we'll do an example of principal stresses, maximum shear stress, and then we'll move on to 3D stresses. Roar! All right, that's it for today. Thanks for coming.